Now the white paper moves into alternative blockchain applications. So let's read. The idea of taking the underlying blockchain idea and applying it to other concepts also has a long history. In 1998, Nick Szabo came out with the concept of secure property titles with owner authority, a document describing how new advances in replicated database technology will allow for blockchain-based systems for storing a registry of who owns what land, creating an elaborate framework including concepts such as homesteading, adverse possession, and Georgian land tax. However, there was unfortunately no effective replicated database system available at the time, and so the protocol was never implemented in practice. In 2009, however, once Bitcoin decentralized consensus was developed, a number of alternative applications rapidly began to emerge. Okay, so not much to say about this. I haven't heard about this concept of secure property title with owner authority. But let's see what they mention here. Namecoin. I heard about Namecoin. Namecoin, it's a distributed domain name thing. Okay, created in 2010, Namecoin is best described as a decentralized name registration database. In decentralized protocols like Tor, Bitcoin, and Bitmessage, there needs to be some way of identifying accounts so that our people can interact with them. But in our existing solutions, the only kind of identifier available is a pseudo-random hash like blah blah blah. Well, this is a Bitcoin address. So, right? Ideally, one would like to be able to have an account with a name like George. However, the problem is that if one person can create an account named George, then someone else can use the same process to register George for themselves as well as impersonate them. The only solution is a first-to-file paradigm, where the first registerer succeeds and the second fails. Okay, a problem perfectly suited for the Bitcoin consensus protocol. Namecoin is the oldest and most successful implementation of a name registration system using such an idea. So if I remember correctly, Namecoin uses Bitcoin transactions and to use the return opcode to store extra information. So the return opcode, I think, should be mentioned later. Okay, no, not really. So the idea here is that scripting is about that probably. The transactions do not actually say from which account to another account goes. It says from which UTXO the source is taken, and there's some script that is stored with the UTXO. What you need to provide is the second part of the script, which then run through the Bitcoin interpreter. So there's some language, there's some rules. The result of running that script is a success. So the first part is in UTXO, which is kind of like the challenge. And in order to spend from that UTXO, you have to provide the answer. So the scripting language that Bitcoin has some operation codes for signature, verifying signature, and also for basic arithmetic. And it has one that essentially is for arbitrary data. It's limited in size, so I think you can only store 20 bytes, 40 bytes, something like that. In the UTXO, and that makes that UTXO unspendable, but it would be part of the blockchain. So Namecoin burns Bitcoin. Basically, you send a small amount of coin to some address, and you put that opcode where you register a particular name. So obviously, Bitcoin doesn't care about this stuff. As long as the scripts are valid, the transaction will be mined normally. So you don't need to send a large, of course you don't want to send a large amount of coins because they are going to be unspendable. There's no way for another user to attach to that UTXO and finish the script to reply to the challenge, because that UTXO challenge has no answer. And so the coins that end up in that UTXO will end up there forever. But it's possible obviously to know which ones they are, and if you put a system like Namecoin on top of it, they can interpret that data as a name and then say that that name belongs to that particular address owner. So color coins now. The purpose of color coins is to serve as a protocol to allow people to create their own digital currencies, or in the important trivial case of a currency with one unit digital tokens on the Bitcoin blockchain. Okay. In the color coins protocol, one issues a new currency by publicly assigning a color to a specific UTXO. And the protocol recursively defines the color of other UTXO to be the same color as the input of the transaction, creating them spend. This allows users to maintain wallets containing only UTXO of a specific color and send them around much like regular Bitcoins, backtracking through the blockchain to determine the color of any UTXO that they receive. Okay, so the idea here is that the UTXO chain, when you create a transaction, you use some UTXO and you create new UTXOs. So normally these UTXOs are just coins, they just have a balance and a certain number of satoshis in there. But if you mark since the blockchain is public, if you arbitrarily say that some original UTXO, some specific UTXOs are of a certain color, between quotes, so it's like a property that you associate with that UTXO, then you can say that you can trace the distribution of this UTXO. So if you take, for example, one UTXO which is you decide is color blue, and then you give it to a guy, he will receive these blue Bitcoins. Of course, nothing really Bitcoin knows about its color, but if you follow the graph, if you follow the provenance, it's like tracing back the origin of your Bitcoins, and you figure out that they come from this blue source, then you will say that they are blue. So that's the idea of color coins. Okay, meta coins now. The idea behind a meta coin is to have a protocol that lives on top of Bitcoin, using Bitcoin transactions to store meta coin transactions, but having a different state transition apply. Different state transition function apply prime. Because the meta coin protocol cannot prevent invalid meta coin transaction from appearing in the Bitcoin blockchain, a rule is added that if apply returns an error, the protocol defaults to no operation. So apply doesn't do anything. This provides an easy mechanism for creating an arbitrary cryptocurrency protocol, potentially with advanced features that cannot be implemented inside the Bitcoin itself, but with a very low development cost, since the complexity of mining and networking are already handled by the Bitcoin protocol. Metacoin have been used to implement some class of financial contracts, name registration, and decentralized exchange. I think, for example, that USDT, the first USDT, was a metacoin. So it was on top of a Bitcoin blockchain. So it was not a token like a Ethereum ERC20 token. I think that now you have another branch of USDT which is a token, but the first version of Tether was on the Bitcoin blockchain. So what you do is you basically do the secret code inside the normal protocol. So kind of like the stuff as I think I said earlier, where you put a secret message inside your normal message. So like the trick where you write a letter where the beginning of each sentence is hides another sentence. So what he says here is that normally if a transaction is invalid, it will be defined as an error, and the transaction would be thrown out, and the block would be thrown out as part of a block. But since Bitcoin doesn't know anything about this secret protocol, then it would be the job of another system, which then looks at these secret messages, decodes them, but it would have to somehow process them, even if the message is nonsensical. So, for example, if you send too many, if you send MetaCoin from an address that doesn't exist, so in this case, it will just simply ignore the transaction instead of declaring an error. Thus, in general, there are two approaches toward building a consensus protocol: building an independent network and building a protocol on top of Bitcoin. Yeah, so that's for the longest time, people prefer to build on top of Bitcoin because you have all the difficulty of implementing a network and mining, and also the fact that with the mining, you have all this hash power that actually secures your network for free between codes, because it's already securing the Bitcoin protocol. It's gonna secure also your own protocol on top. The former approach, while reasonably successful in the case of application like Namecoin, is difficult to implement. Namecoin is actually a different protocol. Each individual implementation needs to bootstrap an independent blockchain. So they created another blockchain, as well as, so that's what I said, and Namecoin is different. I need to look up what it is. I think I'm mistaken with Peercoin. As well as building and testing all the necessary state transition and networking code. Okay, so that's actually really complicated to do, that's right. Networking code is never easy when you have a distributed system, because you're gonna have averse participants. You're gonna have guys who are going to try to mess up with your system, basically. For example, by DDoSing, sending packets, way too many packets, knowing that these packets are actually wrong, but using your resources, wasting your time and energy to basically prove them wrong. And also they can do that in order to block other legitimate nodes from connecting to you. So the fairness in networking is always pretty difficult to solve. Additionally, we predict that the set of applications for decentralized consensus technology will follow a power law distribution, but the vast majority of applications would be too small to run their own blockchain. And we know that there exist large classes of decentralized applications, particularly decentralized autonomous organizations that need to interact with each other. So that's the prediction, is that basically it would be too costly to secure your network. All this proof of work costs some money, and if your network is not worth securing, then there will be not enough participant miners incentivized to protect your network. So they think that they're gonna disappear. Basically, they will be too small and then too insecure. There's but there are a bunch of applications that are not. They still need to communicate. So it's not like Bitcoin can work independently. Bitcoin is only for one purpose, which is like managing the currency. But you will have other systems that will still want to be decentralized, but they would want to talk to each other. So it's already kind of the case now, because we want to do. There are so many coins out there, right? So we want to have a system where you can send coins from one blockchain to another, and do that with the safety of not having the transaction broken midway. So the stuff that worse that could happen is that you want to exchange, for example, BTC for Ether. Then the system takes your BTC but never gives your Ether, so you will lose that BTC. The Bitcoin-based approach, on the other hand, has a flaw that it does not inherit a simplified payment verification features of Bitcoin. SPV works for Bitcoin because it can use blockchain depth as a proxy for validity. At some point, once the ancestors of transaction go far enough back, it is safe to say that they were legitimately part of the state. Blockchain-based meta protocol, on the other hand, cannot force a blockchain not to include transactions that are not valid within the context of their own protocol. Hence, a fully secure SPV meta protocol implementation, we need to backward scan all the way to the beginning of the Bitcoin blockchain to determine whether or not certain transactions are valid. Currently, all light implementation Bitcoin-based meta protocol only rely on a trusted server to provide the data, arguably a highly suboptimal result, especially when the primary purpose of cryptocurrency is to relate the needs of trust. Okay, so you have this SPV thing, right? SPV is you give the ability to request for specific transactions if the transaction is very old, so when it has enough blocks afterwards, you will have basically it has number of blocks that you have after your transaction is called a number of confirmations that you have. Right? If you have a lot of confirmations, it means that it will be very difficult for somebody to fork out from that transaction another block and mine sufficiently to switch the other branch, the current branch, towards the fork. Right? So blockchain meta protocol, on the other hand, cannot force a blockchain not to include transactions that are not valid with the context of their own protocol. So, well, I guess here I don't exactly understand what they mean, but what I'm guessing here is that he's saying that as we saw earlier, the meta protocol, you cannot say that the transaction has to be reverted. So you will accept the transaction. So the blockchain will contain even transactions that are not valid. Right. So if you are a MetaCoin wallet, you will have to make sure that you see all the transactions, not only the transactions that are old, that are of a particular depth, because in Bitcoin, if the transaction is in the blockchain, it's a valid one. So if you have enough confirmation, it means that that transaction is really like carved in stone now, so he's going to be valid. In the case of a MetaCoin, it could be invalid. It could be one of these transactions that is like applies 3 equals 0. So for example, if you have a MetaCoin transaction that's double spend the money, but from a source that was very, very old, right? So this apply should fail, right? You are spending a coin that do not exist or were already spent. In the Bitcoin protocol, that would fail, and then the transaction will not be there. Right? But in the MetaCoin, it will be there. So you would have to make sure that is that transaction valid? You don't know. You will have to check whether the input of that transaction are still were unspent. For that, you have to find the source, right? The inputs, and then you have to scan all the way back, basically, because you have no guarantee that that transaction has inputs that were not spent before. You have to verify it yourself. So that's actually a very big problem. It means that you can't have a light node. You can't have a node that only relies on the Merkle tree and these light proofs. You will actually either need to trust a third party, because SPV would not work. You would give you the transaction. You can verify the transaction exists, but you cannot verify if that transaction is not invalid. And of course, using a third party trusting a third party is not very good for cryptocurrency, which tends to say that they don't need trust. Okay, now we are going to the topic of scripting. So briefly talked about this a little bit earlier, but let's see what it says here. Even without any extensions, the Bitcoin protocol actually does facilitate a weak version of a concept of smart contracts. UTXO in Bitcoin can be owned not just by a public key, but also by a more complicated script expressed in a simple stack-based programming language. In this paradigm, a transaction spanning that UTXO must provide data that satisfies the script. Indeed, even the basic public key ownership mechanism is implemented via a script. The script takes an elliptic curve signature as an input, verifies it against the transaction and the address that owns the UTXO, and returns 1 if the verification is successful and 0 otherwise. Other, more complicated scripts exist for various additional use cases. For example, one can construct a script that requires signatures from 2 out of a given 3 private keys to validate multisig, a setup useful for corporate accounts, secure saving accounts, and some merchant escrow situations. Scripts can also be used to pay bounties for solutions to computational problems, and one can even construct a script that says something like, "This Bitcoin UTXO is yours if you provide a SPV proof that you send a Dogecoin transaction of this denomination to me," especially allowing decentralized cross-cryptocurrency exchange. Okay, so what we said earlier that about the piggy bank. So these UTXO are contain a certain amount of coins of Bitcoin or satoshis, and they are labeled with a private key. So that's not technically correct. We also said more accurately that what you have is that this piggy bank has a challenge, which is a script. A script is like a little program, but we call it script because it doesn't have all the complexity of programming language. And I can see that this is mentioned later. The script, for example, has no loops. There's no very few conditionals, and basically it's a series of instructions. But there's no way to have all the capability of a real program because of the lack of loops. The good thing about the script is that because it doesn't have a loop, it's fairly easy to figure out how much energy running that script is going to take, right? Because you can see the steps. If you see, for example, step A is take 1, step 2 is add 1, step 3 is add 1, then you can count that there are 3 steps and each step is an addition. If instead you have a loop that says for I equals 0 to n, add something, then you don't know, statically you cannot know how many times addition would take place. So it could take place 1 time if n equal 1, but it could take a million times if n equal 1 million. So, and worse is that there could be a loop that never ends, and basically the program takes infinite time to complete. So that's a problem that actually is unsolvable. You cannot figure out by looking at the program whether it will terminate in a finite time or it will just go run forever. So Bitcoin solves that problem by saying that there are no loops, and therefore you know how long this stuff is going to take, right? What you should do though is give, when you want to spend that UTXO, you need to give another part of script, which is the continuation of the script on the piggy bank. So if the piggy bank says 1 plus 1 equal, and then you have to provide 2, because then the equation is quite basically 1 plus 1 equal 2. Right? So another way to say it is as earlier, it's like a challenge and a response. But in practice, it could be used otherwise. It's more like you start the program and you need to complete the program, and so that the evaluation of all this together will result in a success. So, for example, if the program says, and it's actually the other, if we do it this way, it's actually pretty stupid, because you could always say that, okay, the program begins with whatever you want, and then you continue by canceling all the requests from the guy who started the challenge, and then you give your own success. So in fact, it's the other way, right? You have to provide the first part, and they have provided the end part. So you can't change the end of the story. Right? So let's say this give an example is like giving a story where you know the ending, but you have to provide a beginning that makes sense for the ending. Right? So and one of the most typical challenge like that is to provide the signature so that the verification of your signature matches the transaction. So that would be something like blah 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 blah. So XXXX. This is something that the UTXO doesn't have, and what it has is here's the you have to push your challenge is to provide the data, the signature, and the script would be check the signature. That's pretty much all it has. Right? That the first scripts were essentially that. Afterwards, it became a little bit more complicated, because now the addresses are actually, the scripts are not a public key, but they are hashes of a public key. So the instructions are a bit longer, but essentially it's the same idea. You have to provide the input, the beginning, and the UTXO has the end. And all put together, that should become a success. The evaluation should return success. Let's put it this way. Okay, so however, the scripting language as implemented in Bitcoin has several important limitations. Lack of Turing completeness. That is to say, so Turing complete is this class of languages or programming languages which are Turing complete. And Turing is a very famous logician, mathematician, and he's basically the father, one of the father of computer science. So he has defined a set of operations that if a computer or language has all these operations, it can run a certain class of programs. And essentially all the machines or the programming language that we have today are Turing complete. So it's not too many actually, and one of the most important thing that he has proven is that they are all equivalent. So whether you have talking about C++, C, Java, blah blah blah, all these languages, Python, all these languages are able to solve exactly the same class of problems. But Bitcoin is not the case, because Bitcoin is not Turing complete. It doesn't have these loops right now we are talking about. That is to say, while there's a large subset of computation that the Bitcoin scripting language supports, it does not nearly support everything. The main category that is missing is loops, right? Loops. This is done to avoid infinite loops during transaction verification. Theoretically, it is a surmountable obstacle for script programmers, since any loop can be simulated by simply repeating the underlying code many times with the if statement, but it does lead to scripts that are very space inefficient. For example, implementing an alternative elliptic curve signature algorithm will likely require 256 repeated multiplication rounds, all individually included in code. So, without entering the detail or what this elliptic curve signature algorithm is doing, right? I think it refers to the fact that to verify the signature, you have to multiply like a point by a number, and the number. So it's a bit hard to go easily on that. But essentially, all the elliptic curve crypto algorithm deal with points on the curve, and there is a operation and an addition that combines 2 points together. And the idea of the signature is that you take the known point, the starting point, and your secret key is going to be the multiplier for that point. So since you can add point, you can do A plus B, A and B being points, you get another point C. You can also double the point. You can do the A plus A equal 2A. Right? So by extension, you can multiply a point by a number. So for example, 5A would be A plus A plus A plus A plus A 5 times, right? So at the end, you can do 5A, but you cannot really do A5, A times 5. It's not really like meaningful. So in the verification, at one point, you would want to multiply a large number. So the secret key is a number that has like 256 bits, so a pretty large number, and you want to multiply that number with that point to see if it matches the something, and that multiplication is optimized by a series of addition. So in order to multiply by 8, so 8 times A, you will notice that 8 is 2 power 3, right? So written in binary, 8 takes 3 bits, 1 0 0, and therefore a number that has 256 bits would take obviously 256 bits, right? So the idea here is that if you multiply this number, like this super large number, by a brute force, you would never get there, right? It's 10 power 77 times A. You're not going to add A 10 power 77 times. It's really impossible. But if you repeatedly double it, you will see that you only have to double it up to 256 times, because it's like exponentially growing. So you have 1A, 2A, 4A, 8A, 16A, and it goes very fast, and then you would get to 10 power 77 after 256 rounds. So since you need to do this kind of stuff with the numbers, you will eventually see that you will need to do a multiplication by 256, right? And that's not really something you can avoid. It's full of math like that in the signature. So the signature algorithm is actually hard-coded in the language of Bitcoin language. There's an operator for that, which is verify using elliptic curve signature. But if it was not, and you wanted to implement it yourself, then you will see that you need that loop, because otherwise you would have to do 256 multiplications, and you will have to do it without the loop. It will have to be like 256 times doubling. And that's not only the only limitation. This is going to be just one part of the stuff. So he's just saying that without loops, technically you could do, instead of doing for I equals 0 to n, you could do add 1, and if I equals 0, stop. If I equal 1, continue, add 1. If I equal 2, add 1. If I equal 3, add 1, and then you do it like n times. That would be the same as doing a loop on n and adding 1. But since you actually unwinding the loop, you are actually specifying each case one by one. It's obviously going to be a really, really large code at the end. The next point made here is value blindness. Okay, so there is no way for a UTXO script to provide fine-grained control over the amount that can be withdrawn. Okay, for example, one powerful use case of an Oracle contract would be a hedging contract where A and B put $1,000 worth of BTC, and after 30 days the script sends So $1,000 worth of BTC, and after 30 days the script sends $1,000 worth of BTC to A and the rest to B. This would require an oracle to determine the value of 1 BTC in USD but even then it is a massive improvement in terms of trust and infrastructure requirement over the fully centralized solutions available now. Yeah, but that's unrelated to Bitcoin. However, because UTXO are all or nothing, the only way to achieve this is through the very inefficient hack of having many UTXO of varying denomination. I see. Okay, so the idea here is that there's no way to split UTXO. So since scripts cannot create transactions, they can only unlock existing UTXO. You can only unlock existing UTXO. You would have to create like change coins. For example, since you cannot split a coin in two, if you have in your pocket $1, $2, $4, $8, $9, and so on and so forth, right? You can use a combination of these to make any denomination but that's still very inefficient compared to only be able to create one an arbitrary value. So that's still possible. It's like a puzzle, but you can see that if any number is representable in a power of 2 in base 2 in binary, and then you would just need these denominations to reconstitute that arbitrary value. So for example, if you're talking about 8, you have 1, 2, 4, 8 as different UTXOs. So you pick up the one that says 8. The next point being made here is the lack of state. So a UTXO can either be spent or unspent. There is no opportunity for multi-stage contract or scripts which keep any other internal state beyond that. This makes it hard to make multi-stage option contracts, decentralized exchange offers, or two-stage cryptographic commitment protocols necessary for secure computational bounties. It also means that UTXO can only be used to build simple one-off contracts and not more complex stateful contracts, such as decentralized organization, and makes meta protocol difficult to implement. Binary state combined with value blindness also means that another important application with row limits is impossible. Okay, so I'm not sure what he means by this part here, decentralized organization, meta protocol, blah blah. But I think it's pretty clear that if you only have a UTXO of a given value, and you only know whether that UTXO is spent or not spent, the level of state that your smart contract can maintain is very limited. So this is like having to write a program where what you have is only a bunch of switches that are either toggle on and off. Technically you can, but it would just be extremely long and tedious. Blockchain blindness. UTXO are blind to blockchain data such as the nonce, the timestamp, and the previous block hash. This severely limits application in gambling and several other categories by depriving the scripting language of potentially valuable source of randomness. Yeah, this is actually a problem in many of the applications where we use the blockchain as a casino, as a dice. The smart contract, the scripting language, does not let you query any data about the blockchain. So it's basically should be able to take the transaction and move it to another block, and whether it was correct in the first block would be correct as in the other block. So I'm thinking that they did it so that transactions are movable. Obviously, if their input is still unspent, and other things being equal. Thus, we see three approaches to building advanced applications on top of cryptocurrency: building a new blockchain, Yeah, of course, using scripting on top of Bitcoin. So this is actually something that is being done now. People have extended the scripting language of Bitcoin by introducing new opcodes, and these new opcodes, as long as they are they don't break the previous transactions, they introduce a soft fork, not a hard fork. And soft forks are easier to stage as for deployment. And building a meta protocol on top of Bitcoin. Okay, so that's one step above scripting. Building a new blockchain allows for unlimited freedom in building a future set, but at a cost of development time, bootstrapping, effort, and security. I'm guessing he's going to advertise that solution, since Ethereum is a new blockchain. Using scripting is easy to implement and standardize, but is very limited in its capabilities, and meta protocols, while easy, suffers from faults in scalability. With Ethereum, we intend to build an alternative framework that provides even larger gains in ease of development, as well as even stronger light client properties, while at the same time allowing applications to share an economic environment and blockchain security. Okay, so this completes the first part, which actually was not at all about Ethereum, but it was only about Bitcoin. So in the next section, we'll be finally beginning with Ethereum.